All right, we have a test on Friday, right? Is this class? Yeah. Um, so that's got to be exam 2. Um, and the topics are everything up through principal stresses. And remember, it's cumulative, so you got to be ready for older questions too. Um, so I'll start with, I'll answer any questions anybody has related to the test, and then when we're done with that, I'll go back to the examples we're working on. Yes. Hmm. Yes. Um, okay, so let's say that you get um, okay, so first of all, right-handed coordinate systems, most likely for everything you'll ever do, you need a right-handed coordinate system. I think there are some uses for left-handed coordinate systems, but it's never come up in anything I've ever done or a class I've ever taken. Um, and the requirement is I dot j has to be equal to k. I think that's enough by itself, but that also means that I, did I say dot cross? I cross k has to be equal to negative j because the y-axis always has to be the weird one. And then j cross k is equal to I. So that's the definition of a right-handed coordinate system. Um, and so say that you calculate your principal stresses. And you get eigenvectors I'm just going to make up 3 that I know are perpendicular. So let's say you get 0.7071, 0.7071, negative 0.7071, 0.7071, 0, and then 0, 0, 1. Okay, so let's say that you decide to put these in the order. Well, let me draw them. So first of all, here's our original coordinate system. And our principal coordinate system has one axis like this, one axis like this, and then an axis coming out towards us. All right, so let's say that you wanted to align the axes so that your maximum eigenvalue, your maximum principal stress, corresponded to this axis, and you're going to call that, I mean, you can't control which one of these it corresponds to, but say your maximum does correspond to this one, and you want to call that the x-axis, your first one. And then your second one, the middle one corresponds to this, and you want to call that your y-axis. And then the third one corresponds to this, and you're going to call that the z-axis. Okay, so let's say that tentatively you want to go x, y, and then z coming out. well, you can't use that coordinate system because it's not right-handed. If you take the cross product of x and y, you get negative z. Okay. So, and if you wanted to have your z-axis coming out, that's not right-handed. So that's not allowable for any of the math that we're using. So instead, you'd have to either choose a different order, or you could also do it by just flipping the signs of one of these axes. You could use, so if I multiply this one by -1, negative 0.7071, negative 0.707, I'm looking at the wrong one. So this one here, the x-axis, is the middle one I have written here. So I'm going to multiply that by -1. And I get positive 0.7071, negative 0.7071, 0. You know, that's -1 times that one that we were given. You could use that as the x-axis. And then you have a coordinate system that is right-handed, because you have your x-axis this way, your y-axis this way, and now those cross products work. Okay, so when you get those eigenvectors and they give you the directions of the axes, the directions of the principal axes, you can choose, you can use the direction it gives, or you can choose the opposite of that. And you need to do it in such a way that your coordinate system is right-handed. Does that make sense? Mm-hmm. Yeah. Negative 0.94. 342 to be exact. Okay. So that looks like this. So that first one is this direction. This angle's 20 degrees. The second one is this direction. And so if this is the x-axis, this is the y-axis, the z-axis is coming out. And that's a right-handed coordinate system. But it's not a right-handed coordinate system if you wanted this to be the x-axis and this to be the y-axis or something. I think really the way, yeah, I suppose that's what I do. I mean, really, if you're, all of these are sort of cooked up examples, you know. I'm doing them where the only rotation is in one plane, and so it's sort of easy to draw. But if you're doing this in 3 dimensions and you really needed to visualize it for some reason, you do it on a computer in some way, plot it in. I mean, now it's pretty easy, I guess, just to go to what's that plotting software everyone uses? Desmos. You could plot those lines in Desmos or whatever, and that could help you visualize. Really, all you're doing is orienting a cube, remember? So, in a way, I mean, we're used to dealing with coordinate systems, but all we're doing as far as the stress is concerned is saying the stress cube has faces here and here, here and here, and here and here, you know. Yes. Yes, because the then you can factor out one of the eigenvalues, and what you're left with is quadratic, and so then it's pretty easy to solve for the eigenvalues even if you don't have eigenvalues on your calculator. So that's why it'll always be that way. Yes, that will always be the way that it is when I make up these problems, because that's the only way I can think of doing it. Because I start with, okay, here's how I make problems. So first, I make up a principal stress tensor. With one diagonal value equal to 0. So let's say -20, -5, 0. Then I rotate the coordinate system. So let's say this rotation matrix is going to be equal to, did you ask, is the 0 always going to correspond to the axis that you rotate around? The eigenvectors, if the one that's like 0, 1, 0 or 1, 0, 0 or 0, 0, 1, if that one's going to correspond to a 0 eigenvalue, is that? It doesn't have to anyways, because I could do this as, I could rotate like about the y-axis in this case, and it would look like, cosine of -16.5 degrees, 0, negative sine of -16.5 degrees, 0, 1, 0, sine of -16.5 degrees, 0, cosine of -16.5 degrees. And so if this is the stress tensor, then my new stress tensor, this is the principal one. Okay, so I'm starting with sigma sub p. And so then the last step is just transforming a principal stress tensor. So this is equal to Q times principal stress tensor times Q transpose. And in that case, we would get something that still had that -5, and then, other stuff in different places. And then, can someone calculate that? Just do that rotation.
Was it -20 for the first option?
Yeah. Okay. So Ellie, give me yours and we'll see if anyone agrees. Okay. Zero. Okay. Zero. So now I know that if I give you this as a starting, just an arbitrary stress tensor, then when you calculate the determinant and set it equal to 0, I know you're going to be able to factor out a sigma. And so then you'll just have to solve a quadratic formula. If I just gave you a random one, if I filled in all those values, just with random numbers in a way that made it a symmetric matrix, then you could have any 3 roots, and then you just have to solve a cubic equation, and there's no formula for that. Any other questions? No more questions? Yep.
Curious what, are you going to ask us a problem like this, for instance, what values are?
Yeah, probably.
And how do we do that?
Yes. You know what? If I ask you to do that, is there anybody that doesn't have a phone that you can go to websites on? Why don't you just use Wolfram Alpha just on your phone? Okay. Just for that one problem, and don't text anyone. I don't mean use your phone to text someone to give you the answers. That's a good, I mean, now I'd have to say no, but if you did that and then later told me like you just misunderstood, I'd probably allow that. Yeah. Yeah, I give a lot of partial credit. I mean, if it looks like you understand what's going on, I'll give full credit for wrong answers. Yeah, there's a lot of stuff that can go wrong. Yeah. Yes, for sure. Yep. So yeah, just, the more work you show me, the more partial credit I can give. Like if you just, at the other extreme, if you just put down answers and no, I don't have any work and the answers happen to be wrong, I can't really give you anything for that. But if you show every step and then I see this is the spot where you just forgot to multiply this by -1 or whatever, like, yeah, you get almost all or all credit for it. Okay, so yeah, figure out how to do that on your phone if your calculator doesn't do it. If not, yeah, I guess you would have to do it by hand, but Or you could just say, if you want to just describe it in general, what you would do, find this. That's better to me than, you know. Oh yeah, that's true. Okay, do that. Whether you have a calculator that does it or not, if you describe in general what you would do, I'll be happy.
We draw you a picture that makes you happy.
No, because I don't know, pictures just make me happy. So, but I don't. But then my job is to give grades based on how well you understand deform. So that's sort of the problem there. If you program a calculator using MATLAB's GUI building function, you can use that calculator on the test too. You make a robust eigenvalue and eigenvector solving program and share it with a class, I'll give you extra credit. Yeah, for 84s and 83s and 86s, any of those. Yes, that would be great. But I should tell you, coming up with a robust one is sort of tricky. But it really, for this stuff, it doesn't have to be very robust. We're not doing anything tricky. I happened to have spent some time doing that once, and it was a pain in the butt. And then later, I found out, like, oh yeah, those are a pain in the butt. Any other questions?
Yeah. So for number 20,
Okay, yeah. You have it there? This only goes up this. Oh no, there it is. 19.
so it would be number 20 you have to figure out the
Yeah, right. Okay, so well, let's just make those up. Okay, so let's say, so strain number 20, and I'm just going to use, so instead of doing the tensile test from number 19, I'm just going to assume that it's steel.
Want the value
Sure.
for
Yeah.
Young's, it's 9.3.
Okay. Okay. And then for 20, it says, assume the linear elastic region for this material continues up to a stress of 1.5 times 10 to the 7th pascals. Okay, so this is stress, this is strain, and our linear elastic region goes up to this value of 1.5 times 10 to the 7. And now we can use Young's modulus to figure out what the corresponding strain is, because Young's modulus is stress over the strain. So 9.23 times 10 to the 10th is equal to 1.50 times 10 to the 7th divided by the strain. So the strain is 1.50 times 10 to the 7 divided by 9.23 times 10 to the 10th. And what do you get? (1.625) times 10 to the negative fourth. And this is, I know that you don't, I know this is very clear in your head what you're talking about, but don't say e to the whatever, because that people take that as the number e, to that power. So just call it 1.625 e negative 4 or times 10 to the minus 4. And okay, so the point where the linear elastic region ends is there. The linear elastic region always goes through 0 stress, 0 strain. So then that's the linear elastic region. I don't know. I'm not sure I would have thought of it, but I sort of like that. And then after this, it would do this, and then blah, That's right. After that, we don't know. It depends on what the material is, how brittle it is, yeah. Yep. I mean, really, all I care about is this. And this is what this class is about. Any other questions? No? Let's stop. We have a test on Friday. That's enough. Don't you think? You too. Okay. Yeah.